Log on, tune in, find out. Another good idea from Cambridge.
Yeah, today I will talk about the tree reconciliation, and this is a joint work with Zhang Luoxin, my host in Singapore. And I know in this audience, everyone has his or her favorite definition of phylogenetic trees. And in this talk, my tree is rooted and binary, and they are leaf labeled, but I didn't require them be uniquely labeled. And for gene tree, is just as Roy said in his talk, it's just an abstract definition. The species tree is just the leaves that are uniquely labeled. And the gene tree is a multi-labeled tree. Like in here, the same label appears, could be the different number of tips. And the main object in this talk is tree reconciliation. And informally, it's just to embed a tree into another, typically embed a gene tree into a species tree. And the motivation, which has been presented in the previous talk and also the talk in Roy, is to study the discordance between gene trees and the species tree. But here, I present a slightly different approach. I'm talking about the mappings between trees, which I want to simplify a little bit of a previous approach. So where the mappings come from? For example, in here we have this coalescent history, and this is a tree of three populations. This is the species tree 1, 2, 3, and A is here. And now we take three individuals from each population. And then, depends on the coalescence history, we can get a gene tree, 1, 2, 3. In this case, there has the same. There's no discordance in terms of the tree topology. But what I want to emphasize here is not only the gene tree topology we are interested or is coded in this coalescent history, because we also know the coalescence of 1, 2 is in this branch. But now the mapping I'm defining is I map this A. This A actually in this scenario is a coalescent event. I map this event to the branch, to the vertex, which is the branch where the event happens. And I map it to the end vertex of this branch. And the same gene tree topologies might have the different mappings. For example, here, although 1 or 2 they're coalescent before the common ancestor is 3, but now the coalescent event is happening in this branch. So I map A here in R in the root of a species tree. So in this case, we can encode the coalescent histories by a gene tree together with a map between the gene trees and the species tree. And it turns out this is not the only way we can get the mappings between gene trees and species tree. Another well-studied evolutionary force behind the discordance is gene duplication and loss. In this case, a gene family, they are involved inside a gene tree by 3 forces. One is speciation, which is by the blue one, and the duplication, which is the black one, and the gene loss. And similarly, we can also get a gene tree from here. This is all the genes survives in each species. And I just map, now this A here is 2, 3, is this speciation. We can map this also to the branch, the vertex where this event happened. And by this way, we can also encode this scenario, which is sort of a little bit more complicated, by a gene tree and a map. And my motivation is to how to unify this approach and get a more simple way of thinking about it. And to this end, I need a little bit notation, which is just I guess everyone knows, which just says there's a poset structures on the vertex of rooted trees. We said V is not bigger than U, and we said U is an ancestor of V, and V is a descendant of U. And we have LU is just the set of labels of its leaves. For example, if this Lx is 1, 2, 3, as simple as this. And then we have common ancestor and the least common ancestor in the classical way. And now the reconciliation is just a map between the vertex of gene tree to the vertex of species tree, which is first is order preserving. That means if U is below V, then FU must below FV. In somehow, this is a structure preserve because we can view a rooted tree as a poset, and this one is just means we preserve this poset structure. But because we are talking about a phylogenetic tree, we have one additional conditions is on the leaves. This can be regarded as some boundary conditions. That is, for each leaf X, the Fx and X must have the same label. And a reconciliation is just can be think about as a map satisfy these two conditions. And the existence of reconciliation between G and S if only if the leaf set of G is a subset of and the leaf set of S. And the LCA mapping, which is studied a lot in this context, is just a map. If you have children U1 and U2, you map to the LCA of the cluster associated with MU1 and MU2, and you can do this recursively. And here is just the example I showed before. Is we can check this actually preserve the leaf and the order and the vertex of G. And one thing is when we get this map, or what kind of cost we need to reconcile using this map, or what kind of information coded. In these deeper coalescent models, the cost is well defined. This is just for each edge of E in S. You think about how many extra lineages it will used in this mapping. That is, if there is k plus 1 distinct edges, UIVI in the gene tree, and this E is contained in the image of this map, then we said that there is k extra lineage, and we set this 0 if otherwise. And the deep coalescent cost is just sum up all those extra lineages. And here's an example. Here, there's 3 extra lineage, so the DC cost is 3. And how can we do for the gene duplication and loss? For the LCA mapping, this is developed a while ago in 1994. So we said there is a cost on an internal vertex U in G, if only if the map, the LCA map MU is equal to MU1 or equal to MU2. Here, U1, U2 are the children of U. And a slightly modification, we can think about this is this condition 1 is equal to 2. This just means the MU1, the cluster associated to MU1 and the cluster associated to MU2, they are not, and they are intersect. The curious thing is the first one can't be generalized directly to our more general settings, but it turns out the second one works. So in here, a duplication event is also associated with U with respect to a general reconciliation F, if only F, the cluster associated to FU1 and FU2, they are not, they are intersect. And then gene duplication cost is just the sum of all these numbers. Here, for example, we have in this root R, we have a duplication event, and in this B, we have another duplication. So the duplication cost in this to reconcile the gene tree and species tree by this mapping is 2. Similarly, we can do for the gene loss cost, which is slightly complicated a bit, because we have to think about 2 cases. One case is this U actually has duplication, or this U doesn't have duplication. And if this is F is LCA, then this P here, which is this common ancestor of FU1 and FU2, they are equal to the previous definition. And the gene lost is just the sum of all these costs on each vertex. For example, here we have LFB is equal to 4, and you can see clearly B is here is this duplication. So we have 4 lost. And okay, that's so far so good. But what's the advantage of talking about those things? One thing is we can talking about a general is we can talking about all reconciliations between G and S. And one nice thing about this set is we have a very natural set on it. Then we just said a reconciliation F prime is lower than F if and only if on each leaf V, F prime is map, F prime V is below FV. This is quite a natural set induced by the set structure on T2 on the species tree. And in this space, there is a unique minimum element. This is just the LCA reconciliation. And this is there is also a trivial maximum element, which just map every internal node to the root of the species tree. And the main result we have is actually these natural poset structures that are sort of compatible with the 3 cost model we introduced above. That is, if we have 2 distinct reconciliation and F prime is smaller than F, then the cost we defined previous, they are more monotonic for the gene duplication cost, gene loss cost, and the deep coalition cost. And one natural corollary, as LCA mapping is the minimum one in this poset, then we know LCA reconciliation is optimal. When I say optimum, it means that's the minimum cost. For all these 3 costs, for the gene duplication cost, gene loss cost, and deep coalition cost, these are some different approach to establish this result. And actually, for the gene duplication case, we have characterizations of those optimal reconciliation. That is, the gene cost of gene duplication cost of F, if they are equal to that of N, if only if on each vertex they either have both have the duplication event or they both don't have. So that will give us some power to actually enumerate those optimal realizations. So to prove the monotonic result, one key observation is here. We can actually localize those vertex which are different to be more precisely, we can define a distance between two mappings just as the Hamming distance sort of way. It means the vertex, the number of vertex in the gene tree, which is such that they have the different images in the species tree. And the nice thing is that if f prime is actually smaller than f, then we know we can find another f star, which is like between them, and such that f star and f, they are equal to 1. There's just one difference vertex. So by this how we can localize the previous theorem just to focus on this special case. If we can establish the theorem for this special case, then it means it holds for the general case. And in this special case, it's relatively easy. So that's the key observation we had. And in maximum parsimony settings, sometimes we are not only interested in the optimal one. First, there might be not the only one which is optimal. And by the characterization we had before, we can find a dynamic programming approach to enumerate all reconciliation such that they have the minimum gene duplication cost. And the monotonic result will also give us a way to enumerate all those reconciliations which are not too far away from the optimal ones. This is a great approach. Because we know the basic idea is we have a structure here. This is a pose set by all reconciliations. And we know the LCA is the middle one, which is optimal. So we only had to, we know the other, the nearly optimal ones, which is defined as this, they are actually connected here. So by a graded algorithm, we can find them all. And that's almost all I want to say. And we find a slightly different framework to study reconciliations. And we show these three cost measures we studied are actually monotonic. And the algorithms we mentioned are implemented. And here I want to thank the organizers Tandy, Mike, and Vincent, because especially I was introduced in these fields in 2007 in exactly here. So I very appreciate them. And I also thank the Institute and also for your attention. Thanks.
Thank you. Other questions? Yes, Vince.
Does that pose set have any other nice structure?
Yeah, that means on the set of all reconciliations, there's a very nice structure.
But does it have any nice properties, that pose set, other than?
That's a good question. As we said here, this pose set is sort of compatible with these three costs. But can we say something more or in a more abstract way? What kind of function, if they satisfy some property, then they will be monotonic with respect to this pose set.
Any more questions? Okay, I guess then we should thank all the speakers of this morning.